darkness, absolute silence, then a low mechanical pulse. Beneath the silent waters of the Pacific Ocean, far beyond the reach of sunlight, something enormous may be unfolding. Satellites orbiting thousands of miles above Earth have detected strange signals, patterns buried deep within seismic data. At first, scientists assumed it was interference, a glitch, a phantom reading. But the signal didn't disappear. It repeated again and again. Research vessels were deployed. Sonar waves descended into the abyss. What they returned with stunned even veteran geologists. A formation, vast, jagged, stretching for what appears to be hundreds of miles along the ocean floor near California. Experts are not calling it a catastrophe, not yet. But they're calling it unusual. And in the world beneath Earth's crust, unusual can be a warning sign. Because the seafloor is not still. It shifts, it strains, it fractures under pressures powerful enough to reshape continents. Most of the time, those movements go unnoticed, hidden beneath miles of crushing water and darkness. But sometimes, for us, the planet whispers before it moves. And right now, instruments suggest it might be whispering again. Black screen, deep bass impact. Title slowly fades in. The Pacific Ocean is vast, ancient, and largely unexplored. Beneath its restless surface lies a landscape more alien than any desert or mountain range on land. A world of trenches, ridges, and fractures shaped by forces older than humanity itself. It's here, in this cold and lightless expanse off the coast of California, that something unexpected began to appear. It started with numbers. Thousands of feet above the seafloor, a research vessel drifted slowly across a mapped survey grid. Onboard computers translated sonar pulses into topographic imagery, building a digital model of the terrain below. The process was routine. Scientists conduct these scans constantly, charting the seafloor inch by inch to monitor geological movement and refine global maps. Most of the time, the results are predictable. Gentle ridges, sediment waves, the occasional volcanic mound. But this time, the data didn't match expectations. At first, researchers thought it was a glitch, a shadow in the data, but scan after scan. The line remained. It appeared as a thin distortion cutting across the digital seabed model. Long, uneven, jagged. At certain angles, it seemed almost like a scar carved into the Earth's crust. Technicians recalibrated the instruments. They re-ran the sweep. They even shut the system down completely and restarted it to rule out software error. The anomaly didn't vanish. If anything, it became clearer. Curiosity shifted to concern. The crew adjusted the vessel's course and performed another pass, this time at a different angle. The sonar pulses descended again, fanning outward into the darkness before bouncing back with fresh data. When the new scan rendered on screen, the room fell quiet. The formation was still there. And it was bigger than anyone expected. What first looked like a short irregularity now stretched far beyond the original survey boundary. The line continued, extending past the edges of the mapped grid as if it had no obvious end. Researchers expanded their scan radius. More passes, more data, more confirmation. The feature wasn't an illusion. It was real. Within hours, preliminary files were transmitted to geologists onshore. Specialists began reviewing the readings, comparing them against historical ocean floor surveys and tectonic models. The immediate question wasn't what it was why it hadn't been noticed before. Some experts proposed it might be an ancient fault line, one that had existed for millions of years but escaped detailed detection until now. Others suggested a more recent origin, a structural shift in the seafloor caused by slow tectonic stress. accumulating deep beneath the Pacific plate. A few researchers raised a third possibility, quieter but more unsettling, that the formation could represent an active fracture zone still evolving in real time. No one agreed. Debates intensified as additional scans arrived. The formation's edges appeared sharp in some sections, irregular in others. Certain segments looked compressed, as if the crust had been pushed together. Other portions seemed slightly separated, hinting at tension pulling the seafloor apart. These conflicting characteristics made classification difficult. Geological structures usually tell a consistent story. This one seemed to tell several at once, and that inconsistency made scientists uneasy. Because beneath the ocean, geology rarely acts without reason. Every ridge, trench, and fracture is the result of immense forces slowly shaping the planet's outer shell. Pressure builds, plates grind, heat rises, stress accumulates for centuries, sometimes millennia, before releasing in a single sudden shift, which raised an unsettling possibility. If this formation was new or newly active, it could be evidence of stress building somewhere deep below. Researchers requested archived satellite altimetry data searching for subtle changes in sea surface height that might hint at movement beneath. They examined seismic records for faint tremors that might correlate with the structure's location. So far, nothing conclusive appeared. No dramatic quakes, no obvious disturbances. Just the silent presence of that enormous line carved into the seabed, waiting. By the time the mapping vessel completed its extended survey, the full scale of the structure began to emerge. Analysts stitched together scan segments into a single composite image. When the rendering finished, the visual stretched across multiple monitors, a single formation, unbroken, vast. Something was there, and it was massive. Far below the rolling waves off California's coast, the Earth does not rest. It shifts, it bends, it presses against itself with a force so immense that mountains rise, continents drift, and oceans widen over time. What appears calm on the surface hides a restless world beneath, a colossal mechanical system made not of gears and pistons, but of stone. To understand what scientists may be seeing on the ocean floor, you first have to understand what lies underneath it. The outer shell of our planet is not one solid piece. It's divided into massive slabs of crust called tectonic plates. Some the size of continents, others smaller but no less powerful. California sits near one of the most famous and volatile boundaries on Earth, where the Pacific plate and the North American plate meet. These plates are in constant motion, grinding slowly past each other at roughly the speed fingernails grow. It sounds harmless, but when masses of rock the size of nations move, even a few centimeters can unleash unimaginable energy. The ocean floor isn't solid ground. It's a shifting puzzle of colossal plates. And when they move, the entire planet feels it. Beneath the Pacific, these plates don't slide smoothly. Their edges catch. They lock together. Pressure builds silently over decades, sometimes centuries, as the plates strain against one another. Imagine two giant slabs of stone pressed together with unstoppable force. They hold. They resist. And then suddenly they slip. That violent release sends shockwaves racing through the crust. Earthquakes powerful enough to reshape coastlines. But earthquakes aren't the only signs of movement. A deep-sea geology reveals a landscape sculpted by stress. There are ridges where molten rock rises from below, trenches where plates dive beneath each other, and fracture zones where the crust tears under tension. These features are not random. They are the fingerprints of planetary forces at work. Scientists study them like detectives, reading the scars of the Earth to understand what it's doing now, and what it might do next. advanced simulations allow researchers to model these stresses in extraordinary detail. On screens inside research labs, digital versions of Earth's crust glow in shifting colours, each shade representing pressure building within the rock. Blue areas remain stable. Yellow zones show strain. Red regions mark places where tension is approaching a breaking point. In some simulations for Sumatra, stress lines stretch across the seafloor like cracks in glass, revealing how force travels through plate boundaries over time, and sometimes those simulated lines resemble real-world formations detected by sonar. But that's what makes the newly mapped structure so intriguing. If it aligns with predicted stress pathways, it could be evidence of tectonic forces redistributing pressure beneath the Pacific. In geological terms, that would mean the system is adjusting, subtly, slowly, but unmistakably. Researchers compare fresh sonar imagery with archived seafloor maps, searching for differences measured in meters or even centimeters, because in geology, small changes can signal massive forces at work. A ridge rising slightly, a trench deepening, a fracture extending just a little farther than before. These are the clues scientists use to determine whether the crust is stable or shifting towards something more dramatic. If this structure is new, it could mean the seafloor is changing right now in real time. That possibility electrifies researchers, not because it guarantees danger, but because it offers a rare glimpse into Earth's hidden mechanics. Most tectonic processes unfold so slowly they're invisible within a human lifetime. To witness one in progress, to actually detect movement as it happens, is like catching a glacier mid-slide or watching a mountain grow before your eyes. Still, awe is only part of the reaction. The other part is caution. Because every fracture, every ridge, every shifting plate is a reminder that the ground beneath our feet and beneath the ocean is not permanent. It is dynamic, alive with motion. And the deeper scientists look, the more they realize how much of that motion remains unseen, unfolding silently in the darkness miles below. Out there beyond sunlight, beyond sight, the planet is always moving. The only question is, what happens when that movement reaches the surface? When scientists detect an unusual formation beneath the ocean floor, their first question isn't, what is it? It's, what could it become? Because deep beneath the Pacific, even subtle geological changes can carry enormous implications. A fracture alone doesn't cause catastrophe, but a fracture under pressure can be the beginning of one. Researchers immediately begin examining worst-case scenarios, not as predictions, but as precautions. One possibility is seismic activity. If the structure marks a stress section of crust, it could indicate tension building along a hidden fault zone. Should that stress release suddenly, the result could be an underwater earthquake powerful enough to ripple across the seafloor. And when earthquakes happen beneath the ocean, the danger doesn't always stay underwater. A sudden shift in the seabed can displace massive volumes of water, triggering tsunami waves that travel across entire ocean basins. In deep water, they move silently and invisibly at jetliner speeds. By the time they reach shore, they can rise into walls of water capable of reshaping coastlines in minutes. That's why tsunami simulations are among the first models scientists run when studying any large seafloor anomaly. Another possibility lies even deeper. Some fractures act as pathways for heat and magma rising from Earth's mantle. These openings can form hydrothermal vents, or in rare cases underwater volcanic activity. Such events may never reach the surface, but they reveal intense forces reshaping the crust from below. None of these outcomes are certain, Most geological structures remain stable for thousands or even millions of years. But experts don't ignore warning signs, no matter how subtle. They analyze, compare, monitor, and wait, because the real question isn't whether the Earth is moving, it's how fast. In science, discovery is only the beginning. Confirmation takes time, and when it comes to something as vast and complex as the ocean floor, time is the one element researchers refuse to rush. Despite the dramatic appearance of the newly detected formation, experts emphasize a crucial point. The data is still being analyzed. Multiple institutions are reviewing sonar scans, satellite measurements, and seismic records, comparing them against decades of archived geological information. Every pixel, every contour, every shadow in the readings must be verified before any conclusion can be drawn. Because in the world of Earth science, appearances can be deceiving. Ocean floor cracks, ridges, and fractures are not unusual on their own. In fact, they are a natural part of how our planet functions. The crust is constantly forming, shifting, and recycling itself through tectonic motion. New seafloor emerges at spreading ridges. Old crust sinks back into the mantle at subduction zones. Between those boundaries, stress lines and fracture zones mark where plates adjust to each other's movement. Many of these structures have existed for millions of years, unnoticed simply because no one had mapped them in detail before. That's why caution matters more than speculation. Scientists aren't panicking, but they are watching closely. Across research centers, monitoring systems remain active around the clock. Seismic sensors listen for tremors too faint for humans to feel. Pressure gauges track minute changes along the seabed. Satellites measure subtle variations in ocean surface height that might hint at motion below. Together, these instruments form a global early warning network designed to detect even the slightest geological shift. So far, nothing suggests immediate danger. No sudden spikes in seismic activity, no rapid deformation, no signals indicating that the structure is behaving unpredictably. Still, researchers know better than to dismiss the unknown. History has shown that Earth often operates on timescales far longer than human attention spans. What looks still today may be slowly evolving beneath the surface. What appears stable may simply be between phases of movement. The planet does not follow schedules, predictions, or expectations. Its processes unfold according to pressures and forces we are only beginning to understand. Because the planet doesn't need permission to change. It just does. And somewhere beneath miles of dark Pacific water, instruments continue listening, waiting to hear what the Earth might say next. Slow, haunting music rises. The screen fades from black to a wide aerial shot of the Pacific at night. Moonlight glimmers across the surface. Beneath it, only darkness. Somewhere beneath miles of water, far below ships, storms, and sunlight, a line stretches across the seafloor. Silent, hidden, immense. It does not announce itself. It does not tremble loudly enough for the world above to notice. It simply exists, etched into the crust of a restless planet that has been shifting, cracking, and reshaping itself for billions of years. Maybe it's harmless. Maybe it's ancient. A scar from a movement long finished. A mark left behind by forces that have already come and gone. Or maybe it isn't finished at all, because deep beneath the ocean, time moves differently. Pressure builds slowly. Stress gathers quietly. And change often begins long before anyone realizes it has started. Right now, instruments are listening, satellites are watching, scientists are waiting. Not for panic, not for disaster, but for answers. And until those answers come, that silent line remains, unseen, unheard, or maybe just beginning to speak. Music fades. Screen cuts to black.